everyone, welcome to lecture 8 of second week. We have been discussing or reviewing the concept of force and displacement method. In the first two classes of this week, we reviewed the force method of consistent deformation, also discussed the method of consistent deformation written in terms of moment, which is 3-moment equation. Now, today we will first review the concept of displacement method. Okay. Now, you see, if you recall, the force method is as name suggests, force are the primary unknown, though we have to, once we compute the static indeterminacy, then identify the redundant, which is the forces, and which is the number equal to the number of static indeterminacy, and then once the redundant forces are identified, then release those redundant forces, remove those release those corresponding kinematic variable corresponding displacement associated with the forces, redundant forces, and then you get the primary structure, the determinate structure. Then you solve the determinate structure for both subject external load and also for the redundant forces, and then apply the compatibility equation to get the additional unknown. Now, here in terms of we will be doing the displacement method is also based on the similar philosophy, but instead of forces, it is the displacement, as the name suggests, the displacements which are taken as primary unknown. Okay. So, but rest of the thing is all the steps that you have in the force method, we have the similar steps in displacement methods as well, but in the force method, the forces, all the methods are all the steps are due to the fact that forces are taken as redundant, and here the similar methods, similar steps we have, but the steps are different because the displacements are taken as primary unknown. Okay. Now, let us try to understand this to the same examples. Okay. Now, this is an indeterminate structure. Now, by just looking at the structure, we can say that the static indeterminacy of the structure is 4. Okay. And again, we also know how to determine kinematic indeterminacy, and again, if you look at the structure, we can say the kinematic indeterminacy of the structure is also 4. Okay. Right. Now, then what we have is actually when we say the kinematic indeterminacy is 4, we neglect the axial deformation in this structure. If the axial deformation is neglected, if we only allow two kind of deformation, one is the transverse deformation and the rotation at any joint, then only we can say the kinematic indeterminacy of the structure is 4. Otherwise, the axial deformation also we need to take into account. Okay, which is we are not taking into account right now. Now, so if we in the force method, if we substitute, if we write the entire all the supports, if we replace them by their equivalent forces, so these are the equivalent forces. Okay. Now, so static indeterminacy of the structure is 4. Then suppose these are redundant forces. So, if we take these as redundant forces, then your structure becomes the primary structure becomes a cantilever beam, right? Cantilever beam, which is A and then B, C, D and E. This is the primary structure. Now, we need to solve this structure 5 times. One is under the external load, and then 4 times for different redundant forces, 4 different redundant forces, and then apply the compatibility at 4 different joints, okay, to get the 4 additional equations. Now, so this is the primary structure for force method. Now, displacement method, as displacement plays the major role. So, let us assume the red one is the deformed shape of the structure. It could be the deformation could be different, but it is just for the demonstration. Suppose this is the deformed shape of the structure. Okay. of this continuous beam. Now, let us take slope at various joints B, C and D R and E are this. Suppose theta BA is the slope at B in segment BA, and theta BC is the slope at B in segment BC, means theta BA is this and theta BC is this. Similarly, theta CB is this and this is theta CD. As far as the compatibility conditions as compatibility at every joints, because of the continuity, we can say that these two have to be same. Suppose we can write that theta B, theta C, theta D, theta E are the slope at various joints. There is no theta A at theta, there is no rotation at A because joint A is fixed. So, therefore, rotation is 0. Now, then so theta B, theta C, theta D are the corresponding rotation, and here the kinematic indeterminacy is 4. There is no indeterminacy here, it is 0. There is no displacement, no rotation here. So, only 4 displacements which can represent the configuration of the structure is rotation at 4 joints. Therefore, kinematic indeterminacy is 4. Okay. Now, these are the redundant. So, in the force method we take By, Cy, Dy, Uy are the redundant, the forces are the redundant. Now, in this case theta B, theta C, theta D, theta E, the displacements at the joints or rotations at the joints are the redundant. So, this is force method and this is displacement method. Now, this is the difference between force and displacement method. Rest of the things, this is the main difference between force method and displacement method, and the rest of the things are just the consequence of this difference. Okay. Now, so let us see what is so in the force method what we do, this becomes our primary variable, okay, and then this is the primary structure with external load. And then how do we get the primary structure or the basic determinate structure? In the case of force method, if we have once we identify the redundant force, we have to remove the redundant force, right. Removing the redundant force means we need to allow the associated displacement, allow the displacement to take place in the structure, associated displacement to take place in the structure. In the case of displacement method, once we have identified the redundant displacements, what we need to do is we need to constrain those displacements. So, that displacement needs to be removed. In the force method, the corresponding forces need to be removed. In the displacement method, the corresponding displacement need to be removed. For instance, here the displacements were theta B, theta C, theta D and theta E, but if we remove them means if we do not allow this structure to have rotation at B, C, D, E, it means the rotation at B, C, D, E are 0. We are making the rotation at B, C, D, E at 0. How can we make that? By assuming there is a fixed support, there is a fixed end at joint B, C, D, E, which is preventing rotation at B, C, D, E to occur. Okay. Now, next is, once this is the primary structure kinematically determinate, this is primary structure statically determinate for the force method. In the case of displacement method, the structure is kinematically determinate. There is no deformation at any end. So, it is kinematic. The kinematic indeterminacy of the primary structure, the basic structure is 0 with external load. Okay. Now, let us, once we have that, then what we do in the force method, we need to solve that problem. We need to solve the basic determinate structure for the applied force and for the redundant forces as well. We have to do the similar thing here. Now, we make this we divide the entire structure into different parts. Okay. We can make it different parts because these ends are anyway fixed end. Now, once we do that, then suppose, so theta B, theta C, theta D, theta E are 0 everywhere, because these are we are making it to be 0. And then suppose MAB is the moment at A and this is MBA is the moment at B in segment AB. F stands for fixed end moment. They are called fixed end moments because these ends are assumed to be fixed. Similarly, we have fixed end moments for BC, CD and DE. Okay. Now, this is the primary structure subjected to the external load. Now, we have to solve the primary structure subject to the redundant forces or displacement as well, and then apply the corresponding equation. Now, this is the these are the fixed end moments. The sign convention taken as clockwise positive is very important. The sign convention that you might have understood in your structural analysis 1, that what sign convention you take. You can take any sign convention. Sign convention has really, it is very subjective. You take your sign convention. Something is positive for you may not be positive for me, may be negative for me, but what is negative for me, I should be consistent with that definition. Similarly, whatever sign convention you take, that is your choice, but whatever you choose, you have to be consistent with that sign convention. Great. Now, once we have that, this is the primary structure with external load. Now, next is the primary structure subjected to the redundant forces in the case of force method. Now, in this case displacement method, the primary structure subjected to redundant displacement. Now, redundant displacements are this. Okay. Now, these are the with redundant displacements. Now, these displacements is these displacement can occur only when if we apply some amount of forces in the structure. Suppose those forces are, these displacements are written in terms of d1, d2, d3, d4 suppose, and suppose the corresponding moments at B, C, D, E are F1, F2, F3, F4. By application of that moments, we can have a deformed shape like this. We can have a deformed shape. We can have a deformed shape like this. We can have a deformed shape like this. Great. Now, this step is very important because it is not only for this week. Rest of the entire course, we will be using this concept again and again. Now, suppose next is we need to. Next is this is the primary structure subjected to external load. This is the primary structure subjected to redundant displacement, right. In the force method, once we have the primary structure, once we have solved the primary structure subjected to external load and the primary structure subjected to redundant forces, next step was apply the compatibility condition at various joints. But here, once we solve the primary structure subjected to external load, primary structure subjected to redundant displacement or rotation, next is to use equilibrium equation to get additional unknown. These are the major difference. We use compatibility equation to get the additional equation. Here it is the equilibrium which gives us additional equation, equilibrium at various joints. Okay. Now, what are the equilibrium at various joints? Here equilibrium at B is, you see, total moment at B is total moment as B is this plus this plus this, F1 plus this, isn't it? And in actual structure there was no external moment, therefore, this plus this should be equal to 0. That is the equilibrium condition. So, F1 plus fixed end moment BA, fixed end moment BC should be equal to 0. Similarly, we can apply equilibrium equations at all other joints. So, this gives us F1 is equal to this. Similarly, we can have equilibrium equation at all other joints, and those equilibrium equations are this. This is for F2, F3 and F4, and these are called equivalent joint loads. You might have, you can recall, these are called equivalent joint loads. Okay. Now, once we have equivalent joint loads, the next is we can write F1. This is the important step. If you recall, we discussed flexibility, we discussed stiffness, and we discussed that their primary role of flexibility or stiffness, they essentially tell you the similar story, but probably the narratives are slightly different. Whether it is flexibility or stiffness, they relate force and the associated displacement, right. Now, but then whether you compute force with a known displacement or you compute displacement with a known force, depending on that you have the you have stiffness or flexibility. In the force method, we used flexibility matrices, flexibility definition, because the forces were unknown and we need to compute the forces based on the known kinematic condition. So, we use flexibility definition, forces is equal to flexibility into displacement. But in the displacement method, the displacements are unknown. We need to compute the displacements with the known kinematic known static condition, and therefore, we use the stiffness definition. Now, what is the stiffness definition? Stiffness definition is, if you recall, if we have a force, that force is equal to stiffness into displacement. Okay. Now, you see F1 is equal to, from this definition here, if you write F1 is equal to, we have, say, we have m. Okay, let us write it first and then we discuss. Let us write F1 as k11 into d1 plus k12 into d2 plus k13 into d3 plus k14 into d4. Now, again let me write the stiffness definition was force is equal to force is equal to k into displacement. Instead of u, let us write it as d, because that is the symbol we will be using now. F is equal to k into d. Now, if you recall the spring problem where you have just one force and one associated displacement, it is a scalar equation. But if you recall the other problem where you had several forces and several associated displacement, then this equation is not a scalar equation. These equations is essentially a matrix equation, right. The force is a vector, then displacement is a vector, and stiffness is a matrix, which is called stiffness matrix. Okay. Now, in this case, there are 4 components of forces, say F1, F2, F3, F4. So, F here is F1, F2, F3 and F4. Okay. And this is, and D here are the 4 components, one is theta B, theta C, theta D, theta E, or D1, D2, D3, DT, D4. So, D1, D2, D3 and D4. So, naturally, if we have to relate F1, F2, F3, F4 and to D1, D2, D3, D4, we need a matrix K, which is a 4 by 4 matrix. And suppose the elements of that 4 by 4 matrix is K11, K12, K13 and K14. Okay. So, similarly we can write F3, F4, F2 the same way. So, D1, D2, D3, D1, D2, D3, D4 are the displacements or rotation, okay. And K1, K12 and all these are the elements, all are the elements of this stiffness matrix K. Okay. Now, but once you, what is very important, and that you will that I will keep on telling you throughout the entire course. You see, learning a method is important, absolutely important, but until unless we understand what that method physically tells you, what is the physical interpretation of that method, any step we do here, there is a physical interpretation. Until and unless we understand that, there is no point in remembering these steps blindly. When we say that K1, K2, K3, K4 are the element of that stiffness matrices, what those elements essentially mean. Now, they mean, so we can write that in a matrix form like this, just now we discussed. Now, let us now, this is stiffness matrix, these are very important, this is very important for this course, and this is the building block of the entire course, the matrix method of structural analysis. In this course will be forming this stiffness matrix again and again for different kinds of structure. Okay. Now, going back to my previous point, the physical interpretation of this the stiffness coefficients. Okay, let us see what is the physical interpretation of this column. Now, this column essentially gives you, say, when K11 is multiplied with D1, it gives you F1. So, essentially it gives you, say, F1, if we just consider this F1 is equal to K11 into D1, F2 is equal to K12 into D2, F3 is equal to K13 D3, and F4 is equal to K14 D4, right. What does it mean? Now, this is a stiffness definition. This stiffness definition tells you that if F1, if we apply D1 displacement or rotation, I mean whenever I say displacement in this context, it is rotation only. When D1 is my displacement or deformation, then F1 is the force, and this D1 and F1 is related to K11 when K1 is the associated displacement. If you recall, if you recall in the last class I said, or the last week I said, whenever we say stiffness or flexibility, they do not carry any meaning alone. Always there have to be a force and the displacement, associated displacement, along with the definition of stiffness. Okay, so when we say stiffness, then this stiffness relate which displacement to which force, that is very important. So, K11 relates F1 and D1, K12 relates F2 and D2, or rather, and K13 relates F3 and D3, and K14 F4 and D4. So, means if we apply an unit, D1 is the rotation at B. So, if we apply unit rotation at B, sorry, there is a mistake, this should all be 1, these all should be 1, this should be 1. Okay, great, these all should be 1, right. Yes. Now, if we apply unit displacement at B, means D11 is equal to 1. So, F11 becomes K11, K12, K3, and F2 becomes K12, means F1, F2, F3 becomes their corresponding stiffness. Okay. Now, similarly, if we take D2 means if we apply unit rotation at C, then F11 becomes, means contribution at F11, then this becomes, then contribution at F11 becomes K12 into D2. So, total K1 becomes K12 into D2. Similarly, this becomes K22 into D2 plus K232 D2 plus K42 into D2. So, this is the contribution for D1, this is the contribution for D2, and similarly we have, if we make D3, this will be the unit rotation if we apply, this is the contribution for D3, and similarly if we apply unit rotation at E, then this will be contribution for D4. And then finally, we have an equation like this. So, this is this. Now, in this expression, what are known? In this expression, we calculate the fixed end moments for a given, for instance, for a given structure, given if we have a structure like this and subjected to any arbitrary load, we can calculate fixed end moment. If for a given structure, if it is subjected to say uniformly distributed load, any other load, we can calculate fixed end moments. So, all these fixed end moments are known. Okay. Now, once these fixed end moments are known, then equivalent joint loads are also known, means these vectors F1, F2, F3 are known. This stiffness K1, K2, these stiffness, all these elements of stiffness matrix, they are also known because they depends on the material property and the geometry of the structure. So, they are also known. Only unknown here is the displacement. So, displacement can be computed. So, we have a set of linear equations, and if we solve these linear equations, we can solve for D1, D2, D3, D4. Once you have D1, D2, D3, D4, then like in the force method, once we had forces, the redundant forces, once we have solved for the redundant forces, then we use that redundant force, the information of the redundant force to solve the rest of the part of the structure. And here similar thing we can do, once we have the deformation, then rest of the things we can easily compute. Okay, this is displacement method, and this is very important because this is the concept that will be taking that will be taken further to, or that would be to form a very general method, which is the subject of this course. Okay. So, in the last two lecture of this week, we'll once again we'll discuss the various aspects of displacement methods, how to compute the stiffness of different kinds of structure, what are the and also see what are the stiffness metrics, and then finally form the basis of the our platform will be ready to move further. Okay. Okay, then I stop here today. See you in the next class. Thank you.